acceleration times time is not velocity. It is related, it's related to it, but it's not velocity itself.
Is it speed?
No, it will be a vector quantity.
Moment.
No.
Final velocity?
What'd you say?
Final velocity?
Yeah. In some respects, I would say that's closer to just velocity by itself, but
Initial velocity.
no, now combine the two things you said.
Average velocity.
Wrong combining. All right, what's the formula for acceleration?
Velocity or
The change of velocity over time. The change of time.
So acceleration times the time is
Change in velocity.
change in velocity. Times the change in velocity of A is equal to the negative mass of B times the change in velocity of B. I'm gonna go ahead and write out the change. Actually, you can tell me, what is change? What am I subtracting from what?
final minus initial.
Yep. So that's mass of A, final velocity of A minus the initial velocity of A equals the negative mass of B times the final velocity of B minus the initial velocity of B. Let's go ahead and distribute. Mass of A, V, F, A minus mass of A, V, I, A. This is the longest of all the lines we're writing. Minus mass of B, the final B, plus mass of B, the initial. Quick check. Okay, that's looking right. Questions up to here? Okay, so obviously MV shows up 4 times. It's a lot of writing. Let's go ahead and find something simpler to write instead of MAVFA. So I'm just going to use the letter P. And I'm going to let that equal NV. So that last equation there becomes P A final, or P final A minus P initial A equals negative P final B minus P initial B. The same one, writing similar to my using S over there for sine, C for cosine. I'm now going to get all my initial terms on one side and the final terms on the other, so I'm going to add this to both sides, and I'm going to add that to both sides. So I get P final A plus P final B equals, oh, that should be a plus sign there, equals P initial B plus P initial A. So whatever P is, I know that if I add my total initial value plus is equal to my total final value. So I'm just going to sort of represent that by a giant P, the initial, is equal to a giant P final. And the tradition is, and it's difficult to tell with the letter P, especially the way I write it, the tradition is that the lowercase letter is for an individual object, the uppercase is a total. This is the kind of thing that sets physicists' hearts all a-twitter, and the fact that whatever P is, my total initial equals my total final. This is a conservation law. It's conservation of P. Questions up to here before I actually talk about what some of this means. Throw in a few definitions. Okay. This is momentum. This is a special case, but a pseudo derivation of conservation of momentum. That's the word momentum. This force times time, right here. Notice if we keep trailing, I don't switch sides until I get till after this step. So this left-hand side, this force times time is just equal to the change in momentum. So I can write separately, a separate equation over here, that the force times time is equal to the change in momentum. This has a different name besides force times time and change in momentum. At this point, I typically give what I'll call my most obscure clue. When someone suddenly buys you flowers, that is called
A gift.
apparently you're not up on your 1970s
Oh.
perfume commercials.
Actually, I was gonna say courting, but I don't think.
No, not
Were
that.
they posted at the same time?
Impulse. And the commercial is available on YouTube. Anyway, so if you're asked to find impulse, you can either find it by force times time, like the average force times time, or change in momentum, whichever one you're given information for. Now, for the purist out there, this obviously would assume acceleration was constant. If acceleration is not constant, you have to use calculus, and you can still get to the same place. Also notice over here, I have F. If I solve for the force, that's the change in momentum over the change in time. Momentum is just mass times velocity, so that is the change in mass times velocity over time. If mass is constant, we get F is equal to mass times the change in velocity over the change in time, which is just ma. So basically, it's Newton's third law dressed up. But it does give us the power that if mass is not constant, this is still true. So this is the generalized form of Newton's second law. Questions to hear? All right. You're probably thinking at this point, hey, wow, that's really cool. I love derivations of conservation laws. I'm seeing a couple of looks that say, yes, you nailed it. But how does this help? If I have two things colliding into each other, so let's say I just dropped this mass onto the paper. There's no force between them of any note until it actually makes contact. So my force goes from 0 to something, and then, so the force will increase and then the force will decrease. So it's very difficult, since the force is changing, to actually sort of make predictions using just straight up Newton's second law. What this allows us to do is, I really don't care what's happening during the interaction. I can still predict what happens before and what happens afterwards. For example, I'll take a 3 kilogram mass going to the right at 4 meters per second. I'll take a 2 kilogram mass going to the left at 5 meters per second. They're going to collide and stick together. Something which I, at some point, well, actually, I guess now, I will refer to as a perfectly inelastic collision. Or abbreviated PIC. So afterwards, they are now one object of 5 kilograms. And the question is, what is the velocity? What is the final velocity? I don't actually have to calculate any accelerations or forces. I got momentum at my back. Momentum has my back. All right, questions before we actually get into solving? So we start out with P, I'm going to put a little subscript 3 there to represent the 3 kilogram mass. What is the initial momentum of the 3 kilogram mass?
4 meters a second.
That is the initial velocity.
12. I don't know what the units.
First, how'd you get 12?
3 times 4.
Yeah, momentum, just mass times velocity. So the momentum, initial momentum of 3. So we're used to writing on paper, where I actually have to make contact. I do want to point out that PI3 and P3I mean the same thing. I'm not consistent on that, of which one I put first. This is the initial momentum of mass 3, and this is the initial momentum of mass 3. So it would be the mass, 3 kilograms, times the velocity, 4 meters per second. And you get 12. Based upon the units you're multiplying here, what would the units be?
Kilogram meters a second.
Kilogram meters per second. There you go. There is not a one-word unit for it. Not officially, at least. So let's suppose that you really don't like writing kilogram meters per second. What else could you do? Well, over here, I know that force times time is equal to the change in momentum. So this would have the units of momentum. Well, this combination better also. So a kilogram meter per second is also a Newton second. So you could write 12 Newton seconds. Let's say that's too much to write. And you want to see, can we cut this down more? Yes, but there are rules. If you wish to make up your own unit, rule number 1, don't pick a unit that's already being used in this course. So Natalie, say she wants to honor herself and use a capital N, no, because capital N's already been taken by Newtons. Now, personally, when I do this, I use the letter D. Descartes, when Newton was looking at forces, Descartes was actually doing some work with momentum, as we now know momentum. And so I can define a Descartes, I use a capital D, and I am defining it, that's why there's 3 lines there, so this is equal by definition, a kilogram meter per second. And so while this is written on the board, I can now use this. Now, you don't have to use Descartes, you can use something of your own. Capital D is not being used. It doesn't even have to be a letter. I've had some do a special kind of squiggle that they were consistent on. So with that definition there, I could also write 12 Descartes. However, if I'm erasing this board and I erase this, as soon as this is gone, that's no longer true. Because this is something I am defining, this is not generally accepted. If you talk about Descartes to people outside of anyone who's had me before, they will look at you like you're crazy. It is not an official unit. if on a test or quiz, if you write it at the very top of the first page or at the top before any of the problems, I'm assuming that that definition covers the entire test. If you want to work it for just a specific problem, then you just write it at that problem and it works for just that problem. Computer science, that would be the global versus the local variables. Okay. So we have 12, whichever one you want to use. What is the initial momentum of the 5 kilogram mass? Got stunned at the awesomeness of momentum.
Is it supposed to be?
Oh, 2 kilogram mass.
Okay.
Is that, okay, that was where people were having issues. Or at least one of you. All right, what's the initial momentum with a 2 kilogram mass?
10D.
Sorry, you said,
I just said 10. He finished.
and you said,
10D.
no. It is not.
Negative 10D.
Yeah. As soon as Tate said 12 here, he established a convention. Because he said that was 12, and no one contradicted him, that means to the right is positive. So we were establishing that is the positive direction. Therefore, this has to be negative because it's going in the opposite direction. There's a big difference between two objects hitting each other from the head-on collision versus the rear-ending collision. What is the initial momentum of the system? System being both of those things.
2D.
Just add. You add them like vectors.
Subtract.
And then a question that I've asked many times before on various tests and quizzes, only to be shocked if people would miss it. It's the first day. Some of you might not see it quite yet, but hopefully you will. What is the total final momentum?
2D.
Yes. That's the whole point of that. It's the total momentum beforehand, it's the total momentum afterwards. So I know that momentum is mass times velocity. I have only a single object here, so that's 5 times v final. It has to be equal to 2 Descartes. Or, I didn't write units there, so. So what is the final velocity? All right, for those fraction fans. Did you want to throw some units in there?
Oh, probably 2/5 meters a second.
Yep. It's just a semantics thing. I'm accepting meters a second, but officially it should be per second.
Per second.
Or 0.4 for the decimal fans out there. So, from this, we conclude that afterwards, in this perfectly inelastic collision, that the combined mass is now moving to the right, because our answer is positive, at 2/5 meters each second.
And why is it 5 final equals 2?
I know that momentum is mass times velocity.
Oh yeah.
My momentum is 2, and that's my mass and my velocity.
Yeah.
Any questions? Now, we broke this down piece by piece because we're just starting. If I were not breaking it down piece by piece, this is the way I would write it. Three times 4 plus 5, no, it's 2. 2 times -5 is equal to 5 times V final. That's the way I would write it in short and dirty. 12 minus 10 is equal to 5V final. 2 is 5V final, and then V final, 0.4. So that's in essence what we did over there. I wrote it out in this form because this will be helpful the next problem we do. All right, here we go. So 3, 4, 5, 2. All right. So I'm going to take my 3 kilogram mass, going to the right at 4 meters per second. I'm going to take my 2 kilogram mass, heading to the left at 5 meters per second. And then after, this is before, after the 3 kilogram mass is going to the left at 2 meters per second. The 5 kilogram mass what is the final velocity of the 5 kilogram mass? We're going to go through the exact same steps we went through. Well, not the exact same. We're going to start out with the exact same methods.
Is that supposed to be a 2 again?
That is supposed to be a 2, apparently. I am in that loop here. There we go. What is the final velocity of the 2 kilogram mass? Is the question. Now, this starts out the exact same way as we started out the other problem. We have, what's the total momentum before the collision? Yep.